Hey guys, in this video I'm going to go through this Leetcode 112 path sum. So we are given a root of binary tree and an integer target sum. We need to return a true if the tree has root to leaf path, such that is adding up all the values along the path equals to the target sum. The leaf is defined as a node with no children, so the leaf is like this: 7, 2, and 1. And in this example here, the target sum that we are given is 22. So that comes from this path over here. And for this tree, there's no way to sum it to the target sum, which is 5. That's why we return a false. Same for this one. So I'm going to solve this question by first using a recursive method. And then after that, I will use a iterative method to solve it. So first, a boundary condition where if the given root is none, and there's no way to sum it to the target, and that's why it will be returned a false. And then we can create a recursor function where first we have to specify some terminal condition. If we are at uh, the leaf node, meaning that there are no children, and if the remaining I will define what is remaining later. If the remaining is equal to 0, means that we already find the target sum, the path that sums to the target sum, and we return a true. Otherwise, we return a false if the remaining is not equal to 0. At the same time, we are at the leaf node, and this is where we can do the recursion. And we first initialize the left status and the right status as a null. And if the the left node is not none, and then we can recursively call this function on the left node, and the remaining would be what is already remaining at the beginning minus the current value on the left node, and the same for the right node, and then we keep doing that each recursively. If the remaining at the end equals to 0, means that we exactly find the sum of all the value on the nodes equals the target, and that will return a true. And because we don't care it is at the left branch or the right branch, so we use a OR function. And to trigger this recursive function running, we just run it on the root node, the most the parents of all the child nodes. And then the remaining will be the target sum that we're looking at minus the value of the root node. And this is how we can trigger it running. And we can run that. It is pretty, well, it looks okay. This one again. Yeah, this value changes all the time. Yeah, it runs, and next I'm gonna solve it with a iterative approach. So this is the iterative approach, and so we first have a boundary condition that we talked about. If the root is none, and return a false, because there's no way to sum it to the target sum now. And for the stack, so we need a stack, and then we append a tuple, and that has the root itself, also what is remaining, right? Target sum minus the root dot well, that's what is remaining, but how much we need to sum it to the target. And while there's something in the stack, we pop it off, and what's being popped off the root. We have a variable is a temporary root, and also what's remaining, how much we need to go to the target sum. So this is the termination condition, where if we are in the leaf node, if the leaf node means that the left has no left child, has no right child, also the remaining equal to 0 as we talked about before, and then return a true and terminate the whole thing. Otherwise, you just keep doing the following. So if there is something in the left node, we append the left node, and also the remaining what is currently remaining minus the value in the left node. That package it as a tuple and then append it to the stack, and then we will jump back to the stack and then do it again. So and then we can do the same thing for the right node, and then we keep doing it until we are at the leaf node, and also the remaining equal to 0. If this condition is never met, that means that we cannot find a path that submit to the pocket sum, and then they will return a false. So basically, we don't need this guy. And let's run it. And it works. It looks pretty efficient. And for time complexity, this is a big O of n, because we're just traversing all the possible nodes. In a worst case scenario, if there is no path that give us the target sum, we just traverse all the possible nodes. That's a big O of n. For space complexity, we need a stack to append all the nodes that we are keeping track of. So that will be big O of n as well. And yeah, so that's so much for my solution. I hope you like it. If you do, please like this video and consider subscribe to the channel. And I will see you in the next video. Thank you for watching.